within 15 million years or 20 million years after the extinction event, mammals went from animals that had an average body size of maybe a small rabbit up to something that's similar to living hippopotamuses.
252 million years ago, more than 90% of Earth's species vanished in the worst extinction event in Earth's history. What happened next broke every rule scientists thought they knew about recovery. Life did return, but not quickly, not smoothly, and not in the way anyone expected. The explanation behind how Earth recovered after the Great Dying is more shocking than the extinction itself. The aftermath nobody expected. Let's talk about what happened when the dust finally settled. The planet was unrecognizable. Volcanic eruptions in Siberia had pumped millions of cubic kilometers of lava and greenhouse gases into the atmosphere. The oceans were acidic, oxygen-depleted, and warming. Over 96% of all marine species were gone. But here's where things get weird. When scientists examined the fossil record from the early Triassic period, they discovered something that made no sense about life after the Great Dying. The few species that survived suddenly appeared everywhere on the planet, from the poles to the equator, in every ocean, on every continent. The same clams showed up in Antarctica and at the equator. The same snails appeared in ancient seafloors worldwide. Diversity had been replaced by sameness on a planetary scale. This phenomenon, called taxonomic homogenization, shouldn't have happened, but it did. Even stranger, this bizarre uniformity persisted for millions of years. Ecosystems didn't rebound with new experiments in life or bursts of innovation. Instead, Earth limped along, dominated by a handful of hardy generalists that could tolerate heat, low oxygen, and toxic seas. It was as if the planet had hit a biological reset button, but the system froze before it could fully reboot. For nearly 200 years, scientists struggled to understand why recovery took so long, and why life returned in such a flattened, monotonous form. The answer, it turns out, isn't just about extinction. It's about how extreme environmental stress can lock a planet into survival mode. Earth was struggling to recover, and it would take our beautiful planet a long time to get back on track. The 10 million year delay. Life didn't just recover slowly after the Great Dying, it nearly stalled altogether. Most mass extinctions are followed by a rebound within a few million years, but this one left Earth trapped in biological stagnation for at least 10 million years. The reason wasn't just the scale of destruction, it was that the planet itself had become hostile to recovery. To understand why, scientists had to look beyond fossils and into chemistry. Researchers at the University of North Carolina uncovered a crucial missing piece in the oceans of the early Triassic. Before the extinction, the seas were filled with radiolarians, microscopic organisms with delicate silica skeletons. By pulling silica out of seawater to build their shells, radiolarians quietly regulated ocean chemistry and helped stabilize Earth's climate. After the Great Dying, they vanished completely. That disappearance triggered a devastating chain reaction. With no radiolarians left to absorb silica, the oceans became overloaded with it. Silica-rich waters drove a process known as reverse weathering, in which new clays formed on the seafloor. Unlike normal chemical weathering, which removes carbon dioxide from the atmosphere and locks it away in rock, reverse weathering does the opposite. It releases carbon dioxide back into the oceans and air. Under normal conditions, Earth's climate operates like a planetary thermostat. Warmer temperatures speed up chemical weathering on land, drawing carbon dioxide out of the atmosphere and storing it as carbonate rocks on the ocean floor. Cooling slows the process, preventing runaway ice ages. This feedback loop has kept Earth habitable for billions of years, but the Great Dying shattered it. Early Triassic oceans were flooded with silica, not only from the decay of countless radiolarian shells, but from the complete absence of living organisms to restart the cycle. As reverse weathering intensified, it overwhelmed Earth's natural cooling mechanisms. Each year, more carbon dioxide accumulated, ocean temperatures climbed, acidification increased, and the harsher conditions became, the harder it was for new radiolarians and other complex life to evolve and stabilize the system. Scientists found hard evidence of this chemical trap by analyzing lithium isotopes in ancient rocks. Reverse weathering absorbs lithium in distinctive patterns, and right at the extinction boundary, those isotopes nearly vanished from the ocean record. They didn't reappear for roughly 5 million years, confirming that reverse weathering had dominated the planet long after the extinction itself. The result was a destructive feedback loop. Hot, acidic, oxygen-poor oceans prevented ecosystems from rebuilding, and without diverse life to regulate ocean chemistry, those conditions persisted. Earth wasn't just slow to recover, it was actively resisting recovery. Evidence even suggests that this process began before the mass extinction peaked. Radiolarians may have been in decline before the Siberian traps erupted, with volcanic emissions delivering the final blow to an ecosystem already under extreme stress. The Great Dying, then, wasn't a single catastrophic moment, but the culmination of mounting environmental pressure. Yet, a mystery remains. If Earth's chemistry alone was capable of filtering out nearly all life, why did a few species survive at all, and what allowed them to thrive in conditions that should have made recovery impossible? The physiology of survival in a global furnace. You might wonder how anything survived the conditions after the Great Dying. The answer reveals something profound about how life recovered, or failed to, after the largest extinction in Earth's history. Survival wasn't about being the fastest, the strongest, or the most competitive. It was about having the right physiology at the right moment in a radically altered world. To test this idea, researchers at Stanford University conducted extensive physiological experiments on modern marine invertebrates, clams, snails, and their close relatives. They measured how rising temperatures and falling oxygen levels affected survival, mapping the exact thresholds at which different species began to fail. These experiments revealed how hot the water could get, how little oxygen could remain, and which bodies could still function under those extremes. When scientists overlaid these physiological limits onto climate models of the early Triassic oceans, the pattern snapped into focus. The species that dominated the fossil record after the Great Dying were the same ones whose modern relatives show extraordinary tolerance for heat and hypoxia. These organisms weren't just lucky survivors, they were pre-adapted to thrive in conditions that wiped out nearly everything else. Before the extinction, the oceans were environmentally diverse. Different regions had distinct temperatures, oxygen levels, and salinity, and species evolved to match those local conditions. This created rich biogeographic patterns, organisms with narrow ranges, specialized to particular environments. But after the extinction, those differences collapsed. Greenhouse warming and oxygen loss spread across the globe, making vast stretches of ocean harsh in the same way. A clam adapted to low oxygen in one region suddenly found those conditions everywhere. Species that could tolerate extreme heat and suffocating waters no longer faced environmental barriers. As a result, organisms once confined to specific regions began appearing in fossils from all over the world. Local ecosystems started to look the same no matter where you looked. Regional biodiversity dropped by more than half, replaced by a handful of globally distributed generalists. For nearly 200 years, scientists debated how this global sameness could arise. One popular explanation was ecological release, the idea that with predators and competitors gone, survivors simply spread unchecked. But the Stanford models showed that explanation wasn't necessary. The results didn't require predation, competition, or complex ecological interactions. Environmental filtering alone was enough. The planet itself had become the filter. Rising temperatures, widespread hypoxia, and acidifying oceans acted like a giant sieve, allowing only organisms with specific physiological traits to pass through. The survivors didn't spread because the world became easier to live in. They spread because it became uniformly hostile, and only a few body plans could endure it. This reframes how we think about mass extinctions. The real test of survival isn't the catastrophe itself, but the world that comes after. The species that survive the first year may not survive the first million. After the Great Dying, Earth recovered into a state of global sameness, not because life rebounded quickly, but because the planet remained locked in a condition that favored only the toughest, most adaptable forms of life. A global furnace that chose its survivors by physiology alone. Top predators first. Here's where the story takes another unexpected turn. When paleontologists at the University of Leeds created a global fossil database tracking the early Triassic, they discovered the first creatures to bounce back weren't the ones you'd expect. In normal ecosystem recovery, bottom-dwelling organisms like corals and sponges established themselves first. These foundation species create structure for complex food webs. You'd expect predators to come last, but the fossil record shows the exact opposite. Nekton, free-swimming predators at the top of the marine food chain, recovered first. Within about 5 million years, dolphin-like ichthyosaurs cruised ancient oceans, and coiled cephalopods called ammonoids had diversified into numerous species. These apex predators thrived, while the seafloor remained barren. The bottom of the food chain took a staggering 50 million years to fully recover. The creatures that should have formed the foundation, corals, sponges, bottom-dwelling invertebrates, remained scarce while predators ruled the seas above. The reason has to do with oxygen. Surface waters of early Triassic oceans were constantly mixed by waves, retaining more dissolved oxygen than deeper waters. The seafloor was a dead zone, but mobile predators could swim in the relatively oxygen-rich surface waters. This raises an obvious question scientists are still working to answer. What were these predators eating? If the base of the food chain was decimated, what sustained hungry ichthyosaurs and ammonoids for millions of years? The answer likely involves smaller swimming organisms that don't preserve well as fossils, but the full picture remains a mystery. And speaking of creatures that were suddenly wiped out from the planet, what happened to the silica-rich radiolarians? Their sudden disappearance triggered Earth's biological reboot. These tiny organisms had quietly regulated ocean chemistry for millions of years, and when they vanished, the system reset. But why did they vanish at all? The missing radiolarians. Here's the mystery that still haunts researchers. What killed the radiolarians in the first place? These microscopic organisms had thrived in Earth's oceans for hundreds of millions of years. They'd survived previous environmental changes and mass extinctions. Their silica shells were intricate lattices that looked like tiny glass snowflakes. And then, suddenly, they were gone. Evidence suggests radiolarians began declining several million years before the main extinction event. By the time the Siberian traps reached peak eruption, radiolarians had already disappeared from the fossil record. This timing is crucial because it means the reverse weathering that delayed Earth's recovery began before the worst volcanic activity. What stressed radiolarians to extinction ahead of most other species? One possibility is temperature. Radiolarians, like many plankton, have narrow temperature tolerances. As greenhouse gases from early volcanic activity warmed oceans, radiolarians might have been among the first casualties. Their death would have triggered the reverse weathering feedback, which accelerated warming, which killed more temperature-sensitive species, creating a cascade. Another possibility involves ocean circulation. Radiolarians need nutrients that typically come from deep water, upwelling to the surface. If early warming disrupted these circulation patterns, radiolarians could have starved even as other organisms persisted. Some researchers speculate that ocean acidification specifically targets radiolarians. Silica shells are chemically stable in normal seawater, but can dissolve more readily in acidic conditions. If early volcanic emissions acidified oceans before the main extinction, radiolarians might have found it increasingly difficult to build and maintain their skeletons. The most troubling possibility is that multiple stressors combined in ways that specifically targeted radiolarians while sparing other species initially. This would explain why the extinction unfolded in waves. Different groups had different vulnerabilities, and environmental changes played out in a sequence that hit radiolarians first and hardest. Whatever the cause, the loss of these tiny organisms had consequences that lasted for millions of years. It's a stark reminder that the most important species in an ecosystem are often the ones we can barely see. Remove one microscopic piece, and the whole planetary system can spiral out of balance. And when it finally finds that balance again, it's completely different. The long road back. So how did Earth finally escape the crisis? The answer involves time, chemistry, and evolution working together across millions of years. Gradually, newly evolving organisms like sponges began consuming the excess silica in the oceans. As they removed silica from the water, reverse weathering slowed, allowing normal weathering processes to reduce carbon dioxide levels. Ocean temperatures dropped slightly, and cooler water holds more dissolved oxygen. Around 247 million years ago, 5 million years after the extinction, the first hints of recovery appeared. Small patches of seafloor communities began showing increased diversity. By 240 million years ago, meaningful recovery was underway. Temperature gradients between the poles and equator re-established themselves. Different regions developed distinct communities again as environmental conditions diversified. But full recovery took roughly 50 million years. That's longer than the entire history of primates. The creatures that inherited this recovered world were unrecognizable compared to their Permian ancestors. The survivors had evolved in response to the crisis, producing the Mesozoic era, the age of dinosaurs. The ichthyosaurs evolved into dozens of species that ruled the oceans. On land, survivors gave rise to archosaurs, including crocodiles, pterosaurs, and dinosaurs, as well as the earliest mammals. Right now, this ancient catastrophe matters because Earth's oceans are showing changes that mirror the conditions following the Great Dying. Ocean temperatures are rising, oxygen levels are dropping, creating expanding dead zones. Ocean acidification is accelerating. The chemistry is trending in the same catastrophic direction. Current ocean ecosystems depend on microscopic organisms similar to those ancient radiolarians. Diatoms, foraminifera, coccolithophores. These tiny plankton form the base of marine food webs and regulate ocean chemistry. They're already showing stress. If these organisms decline or disappear, we could see a repeat of the reverse weathering crisis. The few species that tolerate warmer, more acidic, less oxygenated waters would spread globally, just as those hardy clams and snails did in the early Triassic. Researchers warn that the current biodiversity crisis could lead to taxonomic homogenization, surpassing even the early Triassic, the greatest such event in Earth's history. We might be creating oceans where only a handful of species survive anywhere, replacing marine life with biological monotony. The key difference is this: the Great Dying was caused by massive volcanic eruptions that humans had no way to stop. Today, we are the ones altering the chemistry of the atmosphere and the oceans. We understand what these changes lead to, and we still have the power to change direction. Every living species today has passed through that narrow survival bottleneck. In a very real sense, we are all descendants of the few survivors. But are we creating the same conditions for another bottleneck right now? Will the organisms we're stressing hold on long enough for us to change course? What would you be willing to sacrifice to prevent our descendants from inheriting a world stuck in permanent survival mode? Tell us in the comments below. Thank you for watching, and see you in the next video.